Welcome to 5.2. Today we're going to talk about definite integrals. Now, if you recall from section 410, an indefinite integral looks like this, and it's a set of functions. For example, the integral of x dx is 1/2 x squared plus c. Now, a definite integral is going to be a number, and the number is this number right here. It's the limit of a Riemann sum. And to illustrate what that is, I'm going to go back to Desmos. Here we've got a curve, and we're approximating the signed area under the curve with the area of these rectangles. And when I say signed area, I mean anything underneath the x-axis, like this red one here, is red, and that gets counted as negative area. But as you can see, if I let n get larger and larger and larger, there's less error between the area of the rectangles and the area under the curve. Now, computing an indefinite integral by taking the limit of a Riemann sum, like this, happens to be very difficult. So let's see if there are other ways to do it. So does this number, first of all, does this number exist? And the answer is yes, if f is continuous. That's all you need is f continuous. Okay, what is the difference between the value of an indefinite integral and a definite integral? An indefinite integral is a set of functions, and a definite integral is a number. So set of functions versus a number. That's a big difference. Are they related? Well, they've got to be. They're both written with this integral sign. It looks very similar. So we're thinking, yes, they're related. So yes, actually they are. And that's the fundamental theorem of calculus, which we'll talk about. The definition, taking the limit of a Riemann sum, looks like a bummer. Is there an easier way? Yes, there's two easier ways. One, areas. And that's what we're going to talk about today. And two, the fundamental theorem of calculus. Okay, before we evaluate definite integrals, let's see some of their properties. Just like derivatives, constants can come out of integrals. Just like derivatives, the integral of a sum or difference is the sum or difference of the integrals. So those are two properties that derivatives have, and they're actually the linearity properties we talked about with finite sums. All right, interchanging the limits. If you want to switch A and B to B and A, you can just introduce a minus sign. And that's because you're going to be integrating backwards. Let me clean this up. Integrating over a single point from A to A gives you 0 because that rectangle there has absolutely no area. And then my favorite one is taking a rest stop. If you want to go from A to B, you're allowed to go from A to C, take a rest, have some coffee, and then pick up and go from C to B. There are a lot of videos in your homework problems that illustrate these properties, and they're really good, so I'm not going to go over them here. Let's talk about the geometric interpretation of a definite integral. As I mentioned before, we want to think of it as the signed area bound by f and the x-axis. So let's look at three integrals over here. The integral from a to b of f of x dx. This is the area of region A, because going from A to B, the curve lies above the x-axis. So this is considered positive area. The integral from B to C, so that's going from this point to this point, is going to be negative the area of B. And that's because all the way from B to C, that function is below the x-axis. And then if we go all the way from A to C, we're going to get the area of A minus the area of B. So let's use geometry to find the value of an integral. So the first thing I'm going to do with this example is I'm going to use the property of linearity that we can rewrite this as two integrals. The integral from -3 to 3 of negative x dx plus the integral from -3 to 3 of the square root of 9 minus x squared dx. Because if we're using geometry, it's going to be easier to graph these individual functions rather than the functions put together. So in this first integral, our f of x, let me go down here to my graph, our f of x is negative x. So let's graph that going from -3 to 3. It looks like that. And so the area bound by the curve and the x-axis looks like this. Now, the area below the x-axis, remember, gets counted as negative. And since this function is symmetric from -3 to 3, this first integral is just 0. All right, what about the second integral? So here we've got f of x. I'm going to write y instead of f of x. Y equals the square root of 9 minus x squared. And we want to graph that. So you might want to pause the video and see if you can graph that from -3 to 3. Okay, hopefully you did that. So here's an easier way to graph that function. Square both sides. Y squared equals 9 minus x squared. And move the x squared over. Y squared plus x squared equals 9. And now I hope you recognize that as the equation of a circle of radius 3. But we're not getting the whole circle because we have positive the square root. So we're getting top half of a circle of radius 3. And we want this area here. And that area, so this second integral, is 1/2 the area of a circle of radius 3, which is pi r squared. R is 3, so that'd be pi times 9. So our whole integral is 9 pi over 2. All right, I'm going to have you read average value on your own, but I did do an example of the average value of this function going from -3 to 3. You might want to read through that. Finally, I want to talk about finding areas between curves with definite integrals. So if you want the area bound by f and g, and f is on top and g is below from a to b, you just evaluate this integral, the integral from a to b of f minus g dx. And here's why. Let me make a simpler picture. Suppose this is f and this is g, here's a, here's b. I want this area here. Well, that area is going to be the area under f from a to b, all of that, minus the area underneath g from a to b. That's how you get this formula for area between two curves. It's top minus bottom. I want to finish with two examples, and I should have put the last example first because it's a little more straightforward. So let's do this one first. Write down an integral for the area of the region bound by y equals root 5 minus x squared and y equals 1. And I've got a picture of that region right here. And those two curves, you can check this, but those two curves meet at -2 and 2. So the area is simply the integral from -2 to 2 of the top curve minus the bottom. The top curve is the square root of 5 minus x squared, and the bottom curve is 1. And then dx, don't forget your dx. So that's it. This is top, and this is bottom. All right, now in this picture above, the top curve and the bottom curve switch halfway through the interval. So this is y equals cosine x, and the x-axis is y equals 0. And you can see they flip at pi over 2. So if we want to write down an integral expression for the area of all of this, not counting the pink as negative area, we want the actual area of the blue and the pink, we need two integrals. So the area is going to be the integral from 0 to pi over 2 of cos x minus 0 dx. That's top minus bottom. And no, you don't have to write the minus 0 there. I'm just doing it to illustrate top and bottom. And then we're going to add on the integral from pi over 2 to pi of top curve, which is 0, minus bottom curve, which is cos x dx. And so there is an integral expression for the area. We're not evaluating it because we don't know how yet, but let me just clean it up a little. 0 to pi over 2 of cos x dx minus the integral from pi over 2 to pi of cos x dx. So what I did is I pulled this minus out and wrote it like that. And I just want to point out that this number will be a positive number. And the reason is cos x lies completely below the x-axis from pi over 2 to pi. So this second integral will be a negative number. But this negative here will cancel that out. So you'll have a negative, negative, and that's how you'll get a positive area. Okay, and that is the end of this section.